Hello everyone. In this video, we discuss multi-class classification, where the goal is to generalize binary classification to multiple classes. In this case, we assume that C represents the number of classes that we have, and therefore these labels Y's are from 1, 2 through C. As mentioned before, these labels do not have any numerical value, so technically you can multiply each of them by 2 or 3 or 4 or whatever number we want. The goal is that we need to use C different labels here, and that's why we use this 1 through C. And we assume that C is greater than 2 because we want to focus on multi-class classification problems. In the case of binary classification using logistic regression, we said that, well, we have two possible outcomes. So this is a very similar case to Bernoulli distribution, where we have binary outcomes. If you want to extend these to multiple outcomes or multiple classes, we can use something called the categorical distribution. So for categorical distribution, since we have more than two classes, we need one probability score for each class or each outcome. And we can show this using this vector theta 1 to theta c. So these are the probability scores for each outcome. And we know that since this should be a valid probability distribution or probability mass function, each one should be from 0 to 1. 0 means impossible to occur, and 1 means certain to occur. And the sum of these values in theta should equal 1, right? That's because of the fact that the probability of the entire sample space should be 1. And in this case, we have one of these C possible cases. And we can represent this categorical distribution in a compact form using this notation where we utilize the indicator function. So what we have in the exponent is I of y equals c. So this means that this term is 1 when the true class or label is c. And therefore, in that case, we have this probability, which is theta of that index c. And therefore, this represents the entire categorical distribution that we have. So now the question is, well, how can we get the logistic regression model that we had and extend this to get multiple probability scores? And how many exactly that should be the number of classes that we have? And we can do this using something called the softmax function. So the idea is very much similar to logistic regression in the case of binary classification. First, we find some combination of inputs with some unknown parameters theta, and then we're going to apply the softmax function. And softmax function is very similar to logistic function in a sense that it's going to give us a valid probability score. To decode this and explain this in more details, so what we really do in the case of multi-class classification, we have this input feature vector x, which is of size d, meaning that we have d elements. It's a d-dimensional vector. We are going to multiply this time by a matrix. So we actually have a matrix vector multiplication. X is of size d, and the result should be of size c because we have c classes, so we need to have c numbers, and then we convert them to probabilities, which means that this W, this weight matrix now, is of size C by D. So C is the number of classes, D is the number of features. And the way you can think about this is that each row of W contains weights for one of the classes that we have. So in this case, we have this input feature vector X. We convert this to a C-dimensional vector. And these are the unnormalized scores for each class, and we can think of them as logits because they're before applying that normalization step. And in this case, the normalization is this softmax function that transforms these logits into a valid probability distribution over C classes. So what's the definition of softmax? So if you give a C-dimensional vector, first it's going to find exponential of those numbers. And this is element-wise. So meaning that you find exponential of the first element of A, the second, etc., to the last element, which is this uppercase C. And this ensures that since exponential function is always above the x-axis, that these things are non-negative. And then we also have to take care of the second condition that we have here, that the sum of probabilities must equal 1. And in order to do that, we divide each of these e raised to the, like, let's say a1, a2, ac, by the sum of all these exponentials. So it is very clear here that if we add all these c values, then you get e of a1 plus e of a2 plus e of ac. And that's exactly what we have in the denominator too, which means that this is a valid probability distribution. However, now when we look at each component separately, that's a number from 0 to 1, which means that we satisfy all the conditions to have a valid probability mass function for the categorical distribution. So I have one numerical example to show you how softmax function actually works. Okay, to explain the softmax function, let's say you have a problem with three classes. And what we have here are the logits or unnormalized numbers. And we want to find these softmax scores, which are these probability scores that we find for different classes. So first we're going to find e raised to the power of 3, right? The first number that we have here, which this is what we get approximately if we use 2 decimal points. And then 0.5 and then negative 1.5. So I forgot here, I used negative 1. This is actually negative 1.5. And therefore, we get these numbers. And the way that we convert this, now we use this e or exponential of 3, and then divide this by the sum of these three values. And if we do this, we get 0.91. And then we get 0.08 for the second one. And then for negative 1.5, again, this is mistake here. This is negative 1.5. We get 0.01. So this tells us that there's 91% chance or probability that the data point that we have here belongs to the first class, 8% to the second, and 1% to the third class. So this is very helpful because this means that now we have a classifier that can handle multiple classes, and it tells us about the confidence in model predictions, right? So this means that in this case, the predicted label should be label 1 because there's 91% chance that that's what the input feature vector belongs to. And the question is, well, how can we define a loss function here? So we have done this before for the binary logistic regression, which we said that it was negative log of the predicted probability for the true class. So let's see how this works if we have multi-class classification problems. So cross-entropy loss function in this case can be written as a summation over different classes that we have. And again, we have this indicator function, which tells us whether the true class for the nth example in this case, because we are considering a data set with n data points, is whether C or not. And when it is C, then we have this negative log of the probability that that data point belongs to that class C. And therefore, this is a way that we can measure the distance between the predicted distribution and true one by focusing on the log probability of the correct class. So overall, this is very much like what we had before with the binary cross entropy formula that we have before, because in that case, we have two cases, whether the output was 1 or 0, and then we had negative log of the probability that we assign to class 1 and negative log of the probability that we assign to class 0. So we can easily extend this to multiple classes. So the way that it works is that we have this negative log of the probability that that data point belongs to the true class. And after this, if we use, for example, something like SGD classifier, we just need to find the gradient of this loss function with respect to the parameters, and then everything else is very much similar to what we had before. One thing I want to emphasize here is how we can evaluate the performance of multi-class classification problems. We earlier talked about precision and recall as two important scores. Precision is defined as true positives over true positives plus false positives when we have binary classification and the corresponding confusion matrix. And recall is true positive over true positive plus false negative. So one measures false positives specifically, and the other one false negatives. So in this case, let's look at the iris flower dataset, which is the dataset that we have 3 species of flowers. This is a very simple classification problem. We are going to use logistic regression. We're going to use train test split to divide the data into training and testing sets. And then we're going to use confusion matrix display this time. And we're going to use confusion matrix display from predictions and provide these actual test values or labels and the predicted label. The only difference here is that instead of using the names of these species, I'm using these names A, B, C, because this makes it a little bit easier to understand the structure of these confusion metrics that we have. So you can see that we have very much the same thing as the binary case, except that now we have 3 rows and 3 columns, because in this classification problem, we have 3 classes corresponding to 3 species of a flower. And the main diagonal terms are again the important ones, right? Because this means that we have like 16 data points from class A and all of them are predicted to be class A, so that's perfect. The same thing with class B, right? So we have 17 here. And you can see in this case, so we have 17 data points and that are in this sort of like this element of 2 and 2. But something we have to be careful here, and I was close to miss this, is that we also have 1 here. So this means that we had 18 data points belonging to class B, but 17 of them are correctly predicted to be in class B, and we made 1 mistake, right? So these off-diagonal terms again here, they correspond to misclassifications. And then if you look at the third row, we have 11 data points that they belong to class C, and all of them are correctly they're predicted to be in class C. So one way to evaluate the performance of classifiers like this with 3 classes is to plot the confusion matrix. So that's a really good way of doing this. But we also usually like to have some numbers to explain like these, like matrices and figures and curves. And in order to do this, we can actually define precision and recall in this case of multi-class classification. So remember, in this case, true positives are the metrics on the main diagonal. So these are true positives, means that we correctly classified them. Then the false positives are the metrics on the columns, excluding the ones in the main diagonal. So in this case means that false positives for class A are these cell 2 and 1 and 3 and 1, these two. The same thing for class B, this one and this one, and then for class C. And then false negatives are the metrics on the rows, excluding the ones in the main diagonal. So false negatives for class A, based on this definition, is the one located at row 1 and column 2, and row 1 and column 3, these two. So this way we can define false positives and false negatives. So here we have the numbers, right? So for class A, right, true positives is 16. And then in order to find false positives, we add these two zeros. The same thing for true positives for class B. So we have 17 for true positives. And then for false positives, we have 0 plus 0. However, for class C, true positives is equal to 11, but false positives is equal to 1. So based on this information, now we can find the precision and recall. And let's say right now, mainly focus on precision using these values that we calculated. And we can do this in two different ways, what we call as micro averaging and the other one macro averaging. In micro averaging, we compute global scores or we use the global counts. So what this means is that precision is true positive over true positive plus false positive. We add all the true positives both in the numerator and denominator, and then we add false positives. So according to this is 44 over 45, which is this 0.9977. And then for the macro averaging, the difference is that we compute the metrics locally and independently for each class, and then we take the average. So that's the definition of the macro averaging. So meaning that precision for A is defined as a true positive only for A and true positive for A plus false positive for A. So we get the number for precision A, precision B, and precision C, and then we take the arithmetic mean. So meaning that we add them together, divide by 3. And here you get this 0.973. And these two numbers should be very like close to each other if we have a balanced data set. So in this case, you can actually use something called classification report. You provide your true outputs and the predicted ones. And you can see that we have this precision recall F1 for individual classes. Like here, technically we call them A, B, C, but there are 0, 1, 2 because we have three class classification problem. However, you can see that, these are the average results. These are using the macro averaging, right? So the macro is what we found here, which is if we use 2 decimal points, 0.97, or the weighted, this is the micro averaging, the global one is 0.98. However, you can see that if we do not have a well-balanced data set, meaning that if you have more data points in one class compared to the other ones, then these things can be very different. So let's look at one way of creating a synthetic data set. So in this case, we use this make classification from scikit-learn. So you can look at the the description here, but the idea is that we can create whatever number of samples we want and set the number of features and also set other parameters like how separated these classes are. So obviously when they get farther, it's easier to classify them correctly and some other parameters. So this uses some normal distribution to create these classes. So here we use this, make classification, 200 samples, 5 features, the number of classes, we set that equal to 3, the class separation. But one thing that's very important, we set these weights, meaning that 75% of data points belongs to the first class, then 10%, then 15%. So here we definitely have that class imbalance. And then we divide the data into train and testing. We use .fit to train our model and .predict to predict labels. So in this case, if we also show you the number of samples per each class, you can easily see that 75%, 10, 15%. So here I use this np.bin count on the testing labels to just show you that we do have this class imbalance. And this is very important because many real world problems, they do have class imbalance issue, meaning that we have more samples in one class compared to some other classes. And this is because we may not have many representatives from some other classes. And if we can use this confusion matrix display from predictions, provide the testing and predicted labels, now you can see the difference here, right? So you can see that if you look at the first row, we have 46 samples in that class A, which is the majority class, and we correctly classified all of them. However, when we look at class B, we have 6 plus 1, 7 data points, and we couldn't classify any of them correctly, right? So we have 0 on the main diagonal. And you can do this for other rows too. So this shows you overall, now we do not have a great classifier, right? Because of these issues. So obviously you can, print this classification report to get these numbers. Um, but let's look at some of these numbers, how we can find them, right? So in the case that we have this first column, so we have 46 as true positive, and then for the false positives, we have 3 plus 6, which is 9, right? So if we do 46 over 46 plus 9, that's we get this 0.8836, which is almost 0.84 if we have used 2 decimal points, right? So that's the precision you get for this class 0 here. Or I call it class A because I like to use ABC instead of 0, 1, 2. So you understand how this classification report works, right? The main point here is that you can find precision and recall per class locally, and then you can also average this either using the macro average or the weighted average, which is the micro average technically. And you can see that now there is a big difference between these numbers, right? And usually the macro, which is, you average things locally and independently, are smaller here, right? Because, for example, for the second class, is class 1, we can see precision and recall values are zeros, right? Meaning that we have a very, very bad classifier. And this will really, reduce the overall values that we have for precision and recall, and that's why it's important to understand both the confusion metrics and also the way that we have these classification report. I hope you found this video helpful.